All right. As a senior propulsion architect, I've spent the last 2 decades right on the cutting edge of aviation. And today, I want to walk you through something really foundational, the thermal engineering blueprint for our P13 hybrid power system. We're literally defining what the future of eVTOL performance and safety looks like, and it all starts with a problem you can't even see.
When you look at an eVTOL, what do you see? The rotors, the sleek body, but its single biggest challenge? It's completely invisible. So in this explainer, we're going to break down the engineering blueprint for managing the most critical yet hidden hurdle facing electric aviation today, and that's heat.
So the first thing we had to do was completely change our mindset. In this new era of flight, you have to understand that thermal management is no longer just a support system, like the AC in your car. It is the core performance enabler. It's the thing that decides your payload, your range, and whether you're even commercially viable.
Now, what's really fascinating here is the fundamental physics of the problem. A jet engine, right? It runs incredibly hot. That creates this huge temperature difference with the outside air, which actually makes it pretty easy to cool. We call that high-grade heat. But our eVTOL powertrains, well, they're super efficient, which is great, but it means they produce low-grade heat. The temperature difference is small, making it fundamentally, physically harder to get rid of.
And look, this isn't just some abstract engineering puzzle we're trying to solve for fun. A projected growth rate of nearly 18% year over year tells you everything. This is a multi-billion-dollar race. The company that solves the heat problem first wins. And that's exactly why we had to architect a solution that was, well, perfect. So that brings us right to the heart of our challenge with the P13 hybrid system. From an architectural standpoint, the problem was unlike anything we'd faced. We had to manage two totally conflicting physical realities on the exact same aircraft. We started calling it our ice and fire problem. And this diagram, wow, it shows that conflict perfectly. During takeoff and landing, when you need the most power, the engine is scorching hot, way over 100 degrees Celsius. At the exact same time, the high-voltage battery has to be kept chilled, below 45 degrees for safety. And the real kicker? This all happens during hover, when you have zero forward airspeed, making traditional air cooling completely and utterly useless.
So how on earth do you solve that? Well, we attacked it with a top-down, MECE approach that's mutually exclusive, collectively exhaustive. Basically, we broke the problem down into its smallest pieces to make sure we addressed every single variable without anything overlapping. This led us to our solution, a dual-fluid, tri-loop system that physically separates the problems so we can solve each one in the best and safest way possible.
Okay, let's look at the actual blueprint and see how it all fits together. We designed 3 completely independent loops. The high-temperature loop cools the engine using a standard ethylene glycol mix. But, and this is critical, for the mid-temp loop cooling the electronics and the low-temp loop for the battery, we use a specialized, non-conductive dielectric fluid to guarantee electrical safety.
Now, the safety principle behind that fluid choice is absolutely key. For our 800-volt battery system, we don't just circulate the fluid around it. We mandate full immersion in this dielectric fluid. It's basically a non-conductive oil. Why? It's simple. If there's ever a leak, it physically cannot cause an electrical short. We've engineered the risk of a coolant-induced fire right out of the system from day one.
But what about those massive heat spikes during takeoff? For that, we use a couple of advanced tricks. First is something called tab cooling, where we pull heat directly from the electrical tabs on the battery cells, right from the source. Second, we can integrate an optional phase change material, or PCM. The best way to think of it is like a thermal sponge. It's a solid wax that melts, absorbing that huge burst of heat, and then safely releases it later as it turns back into a solid during the much calmer cruise phase of flight.
And you have to understand, our design does so much more than just cool things down. It's an intelligent system. It performs peak load rejection to survive those brutal takeoffs. On a freezing day, it preconditions the battery, warming it up from minus 20 degrees to operational temp in less than 20 minutes. And it even performs after-run cooling to protect the engine's sensitive turbocharger bearings long after the pilot has shut everything down.
This system is a true performance enabler. It's not just dead weight. Through active drag management, it actually reduces the aircraft's cooling drag by over 60% in cruise, which saves a ton of energy. And with waste heat recovery, it recycles that waste engine heat to warm the cabin, saving precious battery power that you'd otherwise have to burn on heaters.
Okay, let's talk about the part that really matters, certification. Safety is completely non-negotiable.
We follow the aerospace industry's incredibly strict RASP 4761 safety process. We analyze every single thing that could possibly go wrong. For instance, losing battery cooling, that's classified as hazardous. But losing inverter cooling, which could mean losing thrust, that's catastrophic. Each of these is then assigned a design assurance level, or DAO, which dictates exactly how rigorously it must be designed and tested.
And we don't just hope it works, we prove it meticulously through a 3-step validation process. We start at the component level, testing a single pump until it breaks. Then we move to the system level on a ground rig we call an Ironbird, where we run full mission simulations and intentionally inject failures to see what happens. Only after it passes all of that does it ever get to fly on a real aircraft.
And this table right here, this is the final exam. These are our non-negotiable, hard and fast red lines. The system is only signed off if it can keep the battery below 55 degrees during a 5-minute hover, maintain insulation above 2 megaohms, use less than 3% of the total power in cruise, and maybe most critically, allow the aircraft to keep flying safely for 10 minutes even after a primary pump has failed. So to be perfectly clear, this blueprint isn't just some collection of cool parts like tab cooling or dielectric fluids. It is a fully integrated, strategic system. Every single component, every line of software is architected to work together as one certifiable solution, designed for performance, efficiency, and above all else, absolute safety. Ultimately, this is the kind of deep systems engineering that builds the foundation of trust and reliability needed to make urban air mobility a real thing. It's disciplined blueprints like this one that will finally answer the question not if we'll have air taxis, but simply when you'll be seeing them in the skies above your own city. Thank you.